Yeah, okay. So this is, I'll just quickly overdo till this point so we have it in the recording. So we stopped till operators. This is where we looked at the various operators will help us perform arithmetic and logical operations in hardware design using Verilog. So the first part is arithmetic operators, plus, minus, star, slash, this, percent, which is addition, subtraction, multiplication, division, and remainder of the two numbers. Relational operators is going to give us, as we just discussed, less than, equal to, greater than, greater than, equal to. So we can compare two numbers if they are less than each other, greater than each other, or less than equal to certain numbers. Equality operators is done if two numbers are equal, you have to use equal to, equal to. If two numbers are not equal, if you want to check if two numbers are not equal, it's not equal to. Then this 3 equal to, we'll see in the example in the subsequent slides what is the difference between this. Logical operators is logically you're performing a logical operation between two numbers. This is complementing or inversion of a number. Logical ANDing, logical ORing. Bitwise operators, if you have more than one bit, let's say there's an 8-bit number and you want to perform a bitwise operation within the same number or across numbers. This is something that can be done. So this is a single AND. If you see the difference, logical operators, there were two AND. Bitwise operators, this is single AND. Means what? Basically, if there is, let's say you are doing a 4-bit, there are two 4-bit numbers, and you want to do a bitwise ending with each other. So, bit number, let's say A, there are two numbers A and B. A is 4-bit, B is 4-bit. So, A0 will be ANDed with B0, A1 will be ANDed with B1. So, position wise ANDing will happen. Bitwise AND. That's how bitwise operators work. So the same position, bit number 0 of one number will be ANDed in this case with bit number 0 of the other number. Bit number 1 ANDed with bit number 1 of the other number. This is how bitwise operators work. And there are all these various operators. This is the inversion, this is ANDing, this is ORing. This cap sign is meant for XOR operation. So this is a XOR logic and XNOR logic. So inversion followed by XOR is XNOR logic. Then you have something called unary reduction operators. So if you want to perform this bitwise operation within the same number, so just single number you want to perform a bitwise operation, unary reduction operators are used. We'll see, we have example of this. This might be slightly tricky to understand, but we have example of this. Shift operators, right shifting, left shifting. So you can shift your data right by certain amount of time, left by certain amount of time. Conditional operators, we'll be using a lot of these conditional operators, question mark and colon. We'll see the examples in the subsequent slides, how these conditional operators are used. And concatenation. Concatenation of two numbers can be done using this curly braces. This is called a curly brace. And we can concatenate, or we can basically join two numbers using a concatenation operator. So for example, if you have two 4-bit numbers and if you concatenate them, you will get an 8-bit number. To concatenate two numbers, you have to use this curly braces as we see. So these are various operators available in Verilog. And apart from this one, the triple equal to and this one, apart from this, everything else is synthesized. So we can convert, we can make, we can generate hardware out of the rest of the operators.
Okay.
So this is just another slide with the same thing. We can, this arithmetic, shifting, concatenation, unary reduction, logical. Yeah, so that's, yeah, so this is the example we'll see, which will help you understand. Logical operators. Now, we have given two numbers, A and B. A is 1011, B is 0010. This is a binary 4-bit number, A and B. If I want to perform logical operations on this two number, A logically OR with B, any number, if you result of, so the thing, and A logically AND with B, the result of AND operator is 1 if none of the operands is 0. Operand is A and B. The result of logical OR operator is 1 if at least one of the operand is non-zero. So if A is greater than 0 or B is greater than 0, if one of the bits, so if A is non-zero or B is non-zero, finally I'll get this Boolean result 1 or 0. Logical operation will give me this Boolean result 1 or 0. 1 A and B. If A and B, if one of them is 0, your result will be 0. If both are non-zeros, this result will be 1. Will give me Boolean result. Now if I want to perform a bitwise operation, A logically ORed with B. So bitwise means one bit with same bit. This is MSB bit. Right hand side is LSB bit. So one logically OR with 0 will give me 1. One logically OR with 1 will give me 1. Again, it's a logical OR operation. 0 logically OR with 0 will give me 0. One MSB bit, one logical OR with MSB bit 0 will give me 1. So if by bitwise operation I'll get 1011 as my result. If I do a AND, one AND with 0 will give me 0. 0 AND with 0 will give me 0. One AND with 1 will give me 1. And one AND with 0 LSB bit will give me 0. So bitwise A and B will give me 0010 as my result. Okay.
Okay.
Unary reduction operator. Unary reduction operator means we are going to perform a particular operation on the same number. So in this case A, we are saying unary reduction or A. So the OR operation will be performed on the various bits of A. A is 4 bit, and we are doing a logical ORing here. One so successive bits we are going to perform this logical OR operation in this case. One so this is A. One OR with 0 is 1. One OR with next bit is 1. One OR with next bit 1 is 1. Final result is 1. We do this, then we get 1 bit number, 1 bit result. Unary reduction and operator. So same thing I'm going to do with the AND operation on A itself. 1 AND with 0 is 0. 0 AND with 1 is 0. 0 AND with 0. 0 AND with 1 is 0. Finally, you get 0 as a result. So this operation you are performing on the number itself with the successive bits of them. So is this clear? Logical operation, bitwise operation, and unary reduction operation. Hello?
Yeah.
Okay. So
So
yeah,
one question with the unary operation is, so when you're doing a unary operation, so one or with 0 is 1. So you compare the result with the next number.
right. Now let's say we are doing unary reduction OR operator with on the A number. 1 OR with 0 result is 1. Then that
Mhm.
result will be ORed with the next bit 1, which will give me again 1 OR with 1 is 1. That result will then be ORed with the next bit 1. So 1 ORed with 1 is 1. Finally, I get only 1 bit number, which is the final result.
Okay.
So we are reducing the bits using a particular logical operation. That's why it's called unary reduction operator.
Okay.
So you can note it down, and just one quick thing before you note down these details. Uh, we
Mhm.
talked about this triple equal to and not equal to. Now, if you remember, in Verilog, there can be 4 different values that are possible: logic 0, logic 1, x, and z, tri-state value. X is unknown, z is tri-state value. 0, 1, x, and z are possible numbers, possible data values. But so to speak, I mean, you can have this, but ultimately you can have 0 and 1, logic 0 and logic 1. And in certain cases, z, when you're tri-stating, if it's a bidirectional bus, you can use tri-state to you can use the tri-state logic to block one direction of the bus. When you're trying to, for example, perform an equality operator between two numbers which has a x and z in them, apart from the 0 and 1. So for example, A could be 1 0 1 1 and B could be 0x10. Now one number has x in it. Now if I do a equality comparison between two, I have to use 3 equal to sign, not double equal to. In normal case, I would have had to say A equal to B when just ones and zeros are involved in the numbers. Binary number system, basically. If I want to compare A is equal to B, then I have to say A equal to B. But now since B has X in it, A is 1011, but B is 0x10. Let's assume that it is that. If I want to compare those two numbers, then I have to say A equal to B. Then only I can do the equality comparison. Since there is a X in one of the numbers, or there could be a Z in one of the numbers. X only, Z only, or X and Z both in either numbers. If you have that and you want to do a equality comparison or not equal to comparison, then you have to use 3 equal to or not equal to this sign. When we saw this, if you remember equality operators, if A and
Yes.
B are both just binary numbers, I just say A equal to B or A not equal to B, depending on what I'm checking. But if one of the numbers has X or Z in it, then I have to say A equal to B, or if I'm checking for not equal non-equality, A not equal to equal. Okay, you got the difference between the two?
Yes.
Yeah. So you can note down these things in your notes and then we'll go forward.
Yeah, I'm done.
Done. Okay, just give me a second.
Yeah.
Okay, any questions? Got you understood this completely?
Yeah. And
Okay, so conditional operator. So conditional operator is the one another operator that we saw, which will be used very frequently in Verilog. Uh, so right hand side is a digital circuit that we want to implement, which is a multiplexer. It's a 4:1 multiplexer. Since 4 means 2 raised to 2, we have 4 inputs, 2 select lines will be required. That's how a multiplexer works. N number of select lines for 2 raised to n number of inputs and 1 out. So multiplexer is a combinational logic circuit, as we know, which needs 2 select lines, n number of select lines for 2 raised to n number of inputs, and you have one single output. So how does this work? Assign. So this is a continuous assign statement that we have seen outside the always block. We saw one of the examples or in earlier somewhere. I think last class somewhere. Assign. So this is just one statement we are seeing. We are not looking at the module and other things. Assign Z is equal to bracket concatenate. So this curly braces is concatenate S1 and S0. S1 is 1 bit, S0 is 1 bit. If you concatenate them or combine them, you get a 2-bit binary number. 1 bit and 1 bit combined, you get a 2-bit binary number. If this two value is 2 tick, if S1 S0 is equal to 2 tick B00, so this is how it is read. 2 tick B00 means it's a 2-bit binary number. If S1 S0 is equal to 00, then IA question mark IA goes to Z, which is the output. IA is input, Z is output. Colon S1 S0 is equal to 2 tick B01 question mark IB. So if not 00, if S1 S0 is 01, then IB input B goes to output Z. Colon. Else if S1 S0 is 2 tick B10 question mark IC. Else IC input C goes to Z output. Else if select line S1 S0 is equal to 2 tick B11 question mark ID, input D goes to output Z. Else by default there should be some value. 0, 1 tick B0 means 1 bit value because Z is a single bit output. Else by default, if none of this is true, 1 tick binary 0 will go to Z output or Z output. In normal case, when you're dealing with 2-bit numbers, you're dealing with a 2-bit binary number. Binary numbers can be 0, 1. 0 and 1. So the combination for 2-bit number is 0. Possible values are 0, 0, 0, 1, 1, 0, and 1, 1. So we have actually covered all the possible combinations, but you still have to give this default value. That's how it works. That's how the operator works. If none of this is true, actually one of this has to be true if the select line is having 1 and 0. If by default Z gets 0, 1 tick B binary 0. So using, if I convert this part of Verilog code and I synthesize it, I should get this multiplexer. Okay.
Okay.
Second example using conditional operator. You see this small circuit on the bottom here. There is again a multiplexer. In this case, it's a 2:1 multiplexer. Only two lines. Input line means I only need one select line. One n is equal to 1, 2 raised to n, 2 raised to 1 is 2. Two inputs, one select line, one out. So if op the select line is equal to add a plus b, the adder output goes to output sum. If op is not equal to add, then the subtractor output goes to sum out. That's how the circuit is supposed to behave. So what's the Verilog for that? Simple one line. Assign s is equal to op equal to add. So check if op is equal to add. If it is equal, this condition is true, question mark, then adder output a plus b will give me adder. This output goes to sum output, a sum s signal. If this condition is not true, then this second value a minus b, which is a subtractor output, goes to s. So you check, question mark means you check for this condition. If condition is true, this value, whatever it is, it could be something single value or it could be a combination of some other operations. This value goes to this assign statement, this signal here. If this condition is not true, then the second value goes to S, this assign state signal. That's how a conditional operator works.
Okay.
Okay.
Mm-hmm.
So you can note down this small example and just put it in your own words in your notes. Okay, done.
Yes, I'm done.
Okay.
Mm-hmm.
Numbers. Uh, we saw the number system examples earlier, and we did a refresher of number systems. So the number system is represented in this format: the size of the number system, tick base of the number system, then followed by the value. So if I say 8 tick D16, what I'm telling by using 8 tick D16, it's basically 16 as a decimal number. D stands for decimal. 16 is represented as a decimal number, and I'm trying to, I'll probably assign this value to some integer, integer value, a signal declared as an integer. I'll assign this value. But when I say 8 tick D16, what I'm trying to tell the synthesis tool now, using this 8 tick value, I'm trying to tell the synthesis tool that don't allocate more than 8 bits to save this number. Okay, so 8 tick D16. 16 is a decimal number. I'm going to save it in one of the integers, but by using 8 tick D16, I'm telling the synthesis tool don't use more than 8 bits to allocate to save the number. 16 actually requires only 5 bits to save 16. Now, when you say 8 tick D16, that means you are allocating 8 bits to save the number. So, what is the maximum number possible? If I, what is the maximum number that I can save using 8 bits? Maximum decimal number, you can say. So, if you go back and refresh your number system part of the digital logic,
256 in decimal.
right? So 255 actually, because 255 down to 0, it's always one less, uh, 2 raised to n minus 1, right? So 255 down to 0. So the maximum number I can save is 255 using 8 bits. So what I know is, since I'm designing my system, I know my number will vary, not go beyond 255. That's why I'm telling the synthesis tool that even though right now I'm trying to maybe save 16 in the integer, the signal, which is integer data, don't allocate more than 8 bits because I don't expect this number to go beyond 250. So these are kind of things you can do, and the synthesis tool will then limit the width of that number. Otherwise, the synthesis tool allocates 32 bits to it. If I declare a signal as an integer and I just assign a value, internally the synthesis tool will allocate 32 bits for me. If I do this, 8 tick D16 synthesis tool knows that the designer is telling me don't use more than 8 bits because the number may not go beyond 250. Okay, so 16 will be saved internally as binary using 8 bit number system format. Then 8 tick
Okay.
H0, H stands for hexadecimal number. 8 tick B00010000. So this is the binary number 8 bit. 8 tick O20, this is the octal number. And anyway, we don't deal with octal numbers, either we will deal with decimal or hexadecimal, because binary numbers up to 8 bits is fine. When it goes 16 bits or 32 bits, to read this 16-bit binary number or 32-bit binary number is very difficult. So in those such cases, the binary will be converted to hexadecimal, and then we will use the hexadecimal numbers. So either you will deal with the decimal or hexadecimal numbers in your designs most of the time. Binary is used, but only for smaller numbers, 8 bits or below. If it goes beyond 8 bits, it's better to use hexadecimal numbers. It's easier to read and easier, and you always do it the right way without forgetting a bit somewhere here. So now, if you convert 16 to hexadecimal and to binary, what will that be equivalent?
You said 16 in hexadecimal and binary, right?
Decimal 16, I want to convert equivalent hexadecimal and equivalent binary. Same number, decimal 16.
So 16 would be 10 in hexadecimal, and in binary it would be 10000.
What will be the binary? Sorry,
10000.
I want a 8-bit number. So if
You
you
can you just have to add zeros before the one, probably 30.
3010000. Okay, and can you explain how you came to this conclusion? In hexadecimal, it is 10, and the other thing is binary is this number. How did you
You
calculate?
just have to divide the decimal by 16 when you're converting to hexadecimal. So you get 1 and the remainder is 0,
Okay,
1, 0, and for binary you keep dividing it by 2.
okay. So you remember that, and you can. I think you have
Yeah.
practiced enough, so you can get it done. So it's very important. So the reason I'm asking this, it's very important. You have to. You should be very. It should be very easy for you to convert between number system because you have to do it on a very regular basis when you do design. So yeah, it's correct. Decimal 16 is hexadecimal 10. So we just and binary 0010000. If you calculate it this way, decimal number base is 10. 10 raised to 0, 10 raised to 1. Anything raised to 0 is 1. 1 into 6 is 6. 10 raised to 1 is 10. 10 into 1 is 10. 10 plus 6 is 16. The same thing in hexadecimal format. Here the base is 16. 16 raised to 0, 16 raised to 1. 0 into anything, 16 raised to 0 is 1. 1 into 0 is 0. 16 raised to 1 is 16. 16 plus 0 is 16. Binary, it's a 2, a base of 2. 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. 2 raised to 4. 2 raised to 4 is 1 weightage, other thing is 0. 2 raised to 4 is 16 into 1 is 16. So this will give me 00010000. So this is how a number system should work. But to store any of this number, I will ultimately tell the synthesis tool, don't allocate more than 8 bits to save this number. Because ultimately, whether it is represented in decimal or hexadecimal or binary format, I don't expect this number to go beyond 255. Hence, limit it to 8 bits. Otherwise, the synthesis tool will allocate 32 bits for the number. So that is how you can optimize your design. That is called optimization in synthesis. You optimize the design for area in synthesis by limiting these numbers. Okay. Any other questions here?
No.
So these are some of the keywords in Verilog: module, end, module, input, output, in, out, reg, integer, real, time, etc. Begin, end. If you see, all of them are in lowercase. So Verilog is a case sensitive language. So lowercase will be, so the keywords in Verilog language are all lowercase. For example, module, you cannot use module in lowercase, but technically speaking, you can use module in uppercase, capitals. But it is always good since it is a keyword, whether it's in lowercase, but uppercase or lowercase. Don't use module as a name somewhere. This also doesn't make any sense. If your module is the name of the design, right? Module something and then you declare the port list. The name of the design cannot be module. You have to call it something. If it's an AND gate or 2-bit AND gate, call it AND 2. If it's a 4-bit OR gate, call it OR 4. So you have to name the module in a appropriate way. So you can never, first of all, you cannot never call it module lowercase because it's a keyword. But also don't call it module and then uppercase module. That doesn't make sense from a design perspective, and you will also confuse yourself later on. Like just uppercase module, what does it do and where does it go? But this is a list of keywords that are available in Verilog, which are part of language, so you cannot use it anywhere else in the design. Yeah, we just saw that. So Verilog is a four value language number system, or where 0, 1, x, and z are the possible values. X is unknown, so X is a big no-no in design. Why? Because of this issue. When you have something like this, any signal can should have at least one driver. If you remember, that's the rule of a net. X is a net, or this net basically should have at least one driver. But in this case, it is having two drivers or two sources. One source from this side, one source from this side. Now, one source is driving a logic 1 on this net. The other source is driving a logic 0 on this net. When there is 1 and logic 0, there is a collision there and it will create X value. So this net doesn't know whether it will have 1 or 0. So it will just show as X, unknown value. You should never have this unknown values in your design, in your simulation also. Because initially you're going to simulate your design. If you see a X, that means there could be this is called a multiply driven problem, multiply driven net problem. This will be an error in synthesis. In synthesis, it will see that there are two sources on this net and it will give you an error and it will ask you to fix this problem. So if you really have two sources, then you should use some other logic in between to resolve these two sources, because only one value can go to on the net. So you have to resolve the two sources. You cannot just join them and connect it to the net. So use some logic to resolve, either 1 will go to the net or 0 will go to the net, depending on some logic here. Only then it is okay. If you don't do that, you get an X. So 0, 1, X and Z are possible values in Verilog. But technically speaking, you should always operate at logic 0 or logic 1. The Z part is only for tri-state, which is a temporary condition when you're using bidirectional ports. Okay, any questions?
No.
Assignments. Drive values into the nets and registers. So this is a assign equal to is a assignment operator basically. So any changes in the right hand side on a continuous assign statements are evaluated and the left hand side is updated. Assign out is equal to not in. So in will be inverted. This is a not or the inversion sign. In will be in input or input signal will be inverted, and the inverted value will then get assigned to out signal or output value. This is what this means. Right hand side is updated and then assigned to left hand side. Assign reg out is equal to reg in left shift by shift. So shift is some variable or some signal. Let's assume that shift is 3 for now. If shift is 3, reg in, which is some register, will be shifted left 3 times. And after the shifting left happens, the result will then go to reg out, get assigned to reg out. Now that's how this assign statement or this assignment operator will go, or equal to operator will go. It is used to describe combinational logic. It can have operands and operators. If we use this, assign out is equal to A and B, it will implement the AND gate. Assign EQ is equal to A equal to B. We are checking for this. There are two equal to. So we are checking if A and B are equal. So it's a comparator. If it is they are equal, this will result in 1. It's a boolean. It's a logical operator. So it will result in a boolean result, 1 or 0. If A is equal to B, 1 will be generated. If A is not equal to B, 0 will be generated. And that will get assigned to EQ using this assign statement. Wire hash 10 INV equal to not in. We saw one of the examples at the start of the training. In will be inverted and then assigned to INV after 10 time unit delay. So it's an inverter with delay. Inverting the input and assigning it to INV after some delay. Inverter with delay. Wire 7 down to 0 C is equal to A plus B. C is a 8-bit value. 7 down to 0 means it's a 8-bit value. A plus B will give me an adder. And this adder will then, the result of the adder will be assigned to C. This is how equal to or assign operators work. But you should never do assign A is equal to B plus A. So this is something that's sometimes okay in a software programming environment. But for hardware, if you do that, this will generate in a endless loop at some point of time. And your logic will get stuck. Because A is equal to B plus A means it will go in a loop, basically. If you want to do that, then you should say A is equal to B plus C, then update B and C and A accordingly, and again go in a loop. That's how it should work. You can never have A is equal to B plus A. It might, at certain point of time, it might go in an endless loop and stay there. and your design will get stuck. If your design gets stuck, your chip gets stuck. If your chip gets stuck, your product gets stuck. So it basically hangs. So you have to reboot or restart your design or your product or your system for that matter. That's what will happen when you go in an endless loop. So you don't want your design to go in an endless loop, and this is what will help it go in an endless loop. So avoid this kind of loops. Avoid asynchronous design. I will see when we do synchronous design examples. About 90% of your design, or maybe even 95% of your design, will be synchronous, and it should be that way because a synchronous design work with respect to clock, and normally we work with respect to edge of a clock, positive edge or negative edge of the clock. So every edge, every so let's say let's assume a 100 megahertz signal, clock signal. If we have a 100 megahertz clock signal, that means we are going to have a clock cycle of 10 nanoseconds. That means and let's assume that we are working at a positive edge of clock. So every 10 nanosecond, we are going to get new positive edge of the clock. So every 10 nanosecond, your design is going to be re-evaluated, right, with respect to that clock edge, and then appropriate output or results will be generated. So every 10 nanosecond, even if something like this happens somewhere, the design gets stuck, for example, uh, after the next 10 nanosecond, the design will again get re-evaluated with respect to clock, and the appropriate and correct output can be generated. So there is a chance the design comes out of any stuck conditions or any race conditions, anything of that sort. That's why you should use synchronous designs. Asynchronous design, there is no clock, there is nothing. The asynchronous designs, outputs are functions of inputs. Whenever some input changes, the output changes. Internally, there is no reference signal like a clock. If input doesn't change, or if the input or your design gets stuck, and the input changes, since your design is stuck, it is not responding to the changing input, so the output is stuck. So your system is stuck. So avoid asynchronous designs wherever possible. Use synchronous designs, synchronous logic wherever possible. Any questions here?
No.
Blocking, non-blocking. This is okay. Let's do that. Yeah, we can cover it. Okay. So this is a very important concept in Verilog. Blocking assignment and non-blocking assignment. A blocking assignment looks like that. Reg A is equal to Reg B plus Reg C. So this equal to or normal assignment operator used for blocking assignment. Non-blocking assignment is denoted by this angle equal to Reg A angle equal to Reg B plus Reg C. This is the first difference. Blocking, a normal equal to sign is used. Non-blocking, an angle equal to is used. So how is it different from a logical perspective? This is just a Verilog syntax perspective. This is an example. Let's consider this always block for blocking assignment. Always at passage clock begin. So this is my sensitivity list. Every passage of clock, my always block is triggered. Always at passage clock begin. Reg A blocking equal to data. Reg B equal to Reg A. So data will go to Reg A in a blocking format. Means what? Data will go to Reg A, and the design will stop here till the Reg A is updated with the data value. Then it will go to the next line. Reg A then gets assigned to Reg B. The design will stop here momentarily till Reg B is updated with Reg A value. What was Reg A value in the first place? Data. So Reg B will also get data in the same. There is no delay here in between. So in the same time period or the same time window, data will go to Reg A and Reg B, since we are using blocking assignments. Blocking means the design in a way is blocked here till data Reg A is updated with data value. Then again you go to the next line. This is the design is blocked here till Reg B gets updated with Reg A value, which was data in the first place. So Reg B also gets data and the always block. If you consider a non-blocking assignment with the same always block, Always at passage clock begin, same sensitivity is same always block. Red C gets non-blocking data, angle equal to data. This is a non-blocking assignment. So data goes to Red C in a non-blocking format. How does a non-blocking format work? The design is not stopped here momentarily or is not blocked. We say that the data is scheduled to be updated with, or the Red C is scheduled to be updated with the data value at the end of the always block. The updation happens at the end of the always block. It doesn't stop here, it then goes to the next line. Reg D gets Reg C, but now this Reg C is the old value of Reg C, not the updated value, since it's a non-blocking assignment. Reg C will be updated with data value when the always block ends here. So Reg D is scheduled to be updated with Reg C value. If you want data on Reg D, it will happen on the next. So it will go again in the always block. Reg C will be updated. You again go in the always block. Then next time the Reg D will be updated. So there will be a delay of one time unit or one clock cycle for that matter, because it's a synchronous design. On the first positive edge of clock, data goes to Reg C. On the next positive edge of clock, one cycle later, data goes to Reg C, goes to Reg D. So Reg D will get updated with data value after two clock cycles, whereas Reg C will get updated with data value after one clock cycle. So there is a delay in the assignment here because we are using a non-blocking assignment where we are scheduling the updations. If you convert this to hardware, how will it look like? The first one is a blocking one. Data goes to Reg A, then Reg A goes to Reg B, which is data. So data goes to Reg A and Reg B in the same time unit, which is the same clock cycle. Data, these are two flip-flops. Data goes to, this is a Reg A output, Reg B output, flip-flop output. Data goes to Reg A and Reg B on the same clock cycle. There is no delay. Reg A and Reg B will get data after one clock cycle at the same time. In the second case, data goes to, this is the first output is Reg C, this one. So Reg C is updated with the data value after one clock cycle. Clock is common to both flip-flops. Then this is connected to Reg D. So Reg D, which is data again, Reg D will be updated with the data value after two clock cycles. Reg C will get updated after one clock cycle due to this assignment, non-blocking assignment. Then this Reg D will get updated with the data value here after the second clock cycle. Because we are using non-blocking where we are using scheduling of the assignment. Did you understand this concept of scheduling for non-blocking?
Yes.
So we always, when you do hardware design, okay, one is meant for simulation and one is meant for hardware design. I will tell you and I will ask you a question. Now, if you are a designer, a hardware designer, which will you use for simulation purpose? Simulation means software level operation only. And one is used for hardware design, which is meant to work on a chip in hardware in real life environment on a chip. So which method you will use for simulation and which method will be used for design purposes? Can you think about it?
For the hardware design, I would use blocking assignment, and for simulation, I would use non-blocking assignment.
Why is that?
Because when I'm making any hardware, I would see that the hardware is processing things in very less time. So that's why I would implement that in hardware. And for simulation, I can check each and every step is correct, going correct with every clock cycle. So I will use non-blocking assignments.
So I will ask you another question. Can you tell me what a propagation delay of a gate is? Take a simple AND gate, two input AND gate. Okay. So can you define what a propagation delay of the AND gate is?
Mm, I'm not sure.
Okay, propagation delay is the. I will tell you what a propagation delay is. Propagation delay is the delay of a gate. It's a hardware unit. It's a logic, right? And gate is basically a primitive gate, a logic combinational circuit. So there is some delay by the time you apply input and by the time you get output. Delay in between is used for propagating that value from input to output. That's a delay. So that's a propagation delay of a AND gate. Okay, so now knowing what a propagation delay is, similarly you also have propagation delay for flip flops. It's called a clock to Q delay, but technically it's a propagation delay of a flip flop.
Mhm.
Now consider this concept and again rethink what you're trying to think of. And the logical reasoning behind that also. That is important because you only have two choices. You mentioned you have done embedded C programming, right? If I remember it correctly, have you done embedded C programming?
Yeah, yeah.
So have you worked on a switch operation in embedded C programming? Were you
Mm,
trying to read a switch
No,
somewhere?
no, I don't think so.
Okay, because I was trying. What the reason I was asking was there is a concept of debouncing delay in switches.
No, I've
Okay.
not used it.
Anyways,
Yeah.
okay. So let's not sidetrack that. So, so
Mhm.
now so this is another information which I gave you that this flip flop that you see in front of you will also have something called a propagation delay. It's not called propagation delay. It's called clock to Q delay, basically, but it's a delay for operation of a flip flop, and it will have that. So if you know that now, which method you will use for simulation and which method you will use for synthesis or for design purpose, hardware design purpose, and why? Or is your answer still the same? That is also option.
I guess I'll go with the same answer.
Okay. So that answer is wrong, and I'll tell you why it is wrong. So I just explained to
Okay.
you the propagation delay of a gate, or there is some delay for a flip flop to operate, which is the clock to Q delay. When I work with hardware, okay, so yeah, the logical reasoning behind your this answer is good that you want your hardware to operate very quickly or as quickly as possible. But hardware doesn't work that. Any hardware you take, even a simple gate like an AND gate, will have certain non-zero delay involved for generation of output. Ideally, I would like it to work with zero delay as a design, but it will not work like that. After the inputs are applied, there is some non-zero time it will take, which is the propagation delay of that gate. After that time only the output will appear on the gate. Same with the flip-flop. After I apply data input, there is a clock to Q delay, after which the data will appear on the output side. Now take this example. First example, when the data goes to reg A, with in zero time reg A goes to reg B. So basically data goes to reg B in zero time. It cannot work in hardware because this will be a separate flip flop as we see here. This will be a separate flip flop as we see here. The output of first flip flop gets data, then immediately the output of that flip flop will get updated, and we are assuming here it will get updated and that will become input to the second flip flop, and the second flip flop will also get updated. If you look at this statement, always at pos edge clock, so my design is working with respect to edge of a clock, positive going edge, 0 to 1 edge. So by the time data gets assigned to edge reg A flip flop, and then I go and try to take this updated value of reg A and try to assign it to reg B. Technically speaking, my edge is gone, right? My edge of the clock is gone by that time. So technically speaking, on the next clock edge, if you see below, my data will go to reg D, which is what will happen in this case. Data is reg C is scheduled to be updated with data on the first clock cycle. On the on the second positive edge of the clock cycle, this value, reg C updated value, will then go to reg D. So reg D will get data at the second clock cycle end. This is how, due to the inherent delays involved in hardware gates and components, this is how your hardware will work in real life. Now, if you simulate using this method, so if I use this for simulation or use this for simulation, this also simulation will show me one clock cycle delay. This will also show me, this will show me zero clock cycle delay, or just one clock cycle, not two clock cycle, as in this case, only one clock cycle. This is the right way for the bottom one. Non-blocking is the right way for hardware design, which will work on a board somewhere. This is good for simulation purpose because we are assuming zero delay in between the updations in logic. Zero delay doesn't work in real life hardware. Every gate, every component will have some delay involved. And since you are working with edge of the clock, by the time the second edge comes, by the time the second statement comes along, the edge is gone. Red C will not be Red C is updated only at the end of the always block. So by that time, that initial edge is gone. So the initial edge of the clock will only update this first value, let's see, with data. But if I want reg D also to be updated with this value, there will be a one clock cycle delay further, where reg D gets updated after second clock cycle. This is the right way to represent or model in hardware. So see, what is my simulation? Why am I doing simulation here? It is not just because I have some software and I'm running some software, right? Simulation, you have to perform a simulation to check. Ultimately, this is going to be, let's say I'm designing something and it will be implemented on a FPGA or a ASIC somewhere. That's why I will use Verilog. So it's going to go on a hardware system somewhere. But before I go and implement something on hardware, I want to try this design out in my software at a simulation level to see whether functionality and timing, everything is correct. If it is correct at the simulation level, only then I can proceed further. If you remember that FPGA design methodology flow, we started with the design specifications, then we do with Verilog design and test bench, we perform a simulation. Once that is correct, then we go on to synthesis and backend stages. So when I do my simulation, I want to be confident that my design functionality and the timing is okay at simulation level. It should then go and work on my chip level at a hardware level. That's why the second one, non-blocking assignments, will be used for, is better suited for hardware design purpose. Blocking assignments are suited only for simulation purpose. It may work. I will not say it won't work. In certain cases, it may work. In certain cases, it may not. When you are trying to, when your data is changing fast, because the data is going to reg A and then it is going to reg B. The data is changing faster than the clock cycle, or in such cases, it will fail. If the clock is faster than data, if the data is changing very slow, it will still work. But in certain cases, if the data is changing faster, it will not work. So on the safer side, to be more consistent, we will always use non-blocking assignments in our Verilog, whether it is meant only for simulation purpose or for design purpose. We'll end up using only non-blocking assignments in our, because we cannot mix and match. That's one of the rules in Verilog. I cannot have one statement non-blocking and another statement blocking. If I'm using non-blocking, I should use all the non-blocking for all the assignments in my Verilog module, or use blocking for all of the assignments in my Verilog module. So I will end up using, if I'm a designer, I will end up using non-blocking assignments. Does that make sense from a logical perspective?
Yes.
Okay, so you note down these things, note down this example and few points in your own words.
Yes, I'm done.
Done. So this is a very important concept in Verilog, and if you're going for any interviews for anywhere, and you say, "I know Verilog, I've done Verilog design," this is one of the guaranteed questions to be asked, or in your if there is a written exam somewhere or something. So over a period of time, you should refresh this and keep this in mind. This is also a very important question from interview perspective also in Verilog. Okay. Okay, we'll stop here today. Okay, and the next class will be